If you really want to get a grip on where AI is going, sometimes you have to look back at where it all began. So today, we're going to jump in the time machine and explore a truly foundational moment, the story of LeNet-5, a revolutionary architecture that, for the first time, really taught computers how to see. It all kicks off with a pretty simple question, right? How do you teach a machine to read a handwritten number? I mean, it's something a little kid can master pretty easily, but for a computer, it's this monumental challenge of pattern recognition. See, to a machine, this digit isn't a 3. It's just a collection of pixels, a grid of light and dark squares. So how does it learn that this specific arrangement means 3 and not an 8, or maybe even a B? That was the exact problem that one pioneering computer scientist was absolutely determined to solve. And the breakthrough here wasn't about trying to program a computer with endless rules for what a 3 is supposed to look like. No, it was about creating a system that could actually learn on its own. So let's meet LeNet-5. This thing was proposed way back in 1989 by the brilliant Yann LeCun, and it was one of the very first neural networks to use this super clever technique called convolution. Its mission was laser-focused: classify handwritten digits. And it did this by combining that convolutional approach with a powerful learning method called back-propagation, which is, and this is the really cool part, basically a way for the network to learn from its own mistakes, constantly fine-tuning itself to get better and better. All right, so how does this thing actually work? Let's pull up the blueprint. I want you to think of it like a roadmap, a journey that takes a simple, pixelated image of a number and turns it into a confident answer, one step at a time. And here is that map. The LeNet-5 architecture has 7 distinct layers. And as our little handwritten digit travels through this whole system, each layer has a specific job to do. It filters, it shrinks, and it analyzes the information until, bam, a final decision is made. Okay, before we dive in, let's just get the lingo down. It's super simple. C is for convolutional layer, that's our feature hunter. S is for a subsampling, or you might hear it called a pooling layer. Its job is to downsize things. And F is for a fully connected layer. That's what helps make the final call. Got it? CSF. Let's go. All right, our journey kicks off with what I like to call the feature hunt. The network's very first task is to scan the raw image and find the most basic building blocks of the digit. The lines, the curves, and the edges. So first up is layer C1, the first convolutional layer. Now you can imagine this layer as a bunch of tiny magnifying glasses, and they're all sliding across the image. But here's the trick. Each one is trained to spot a very specific, super simple feature, like a little horizontal line or a gentle curve. So let's break that down. What is a convolutional layer? Well, that magnifying glass we just talked about, that's actually called a filter, or a kernel. It scans the image and spits out something called a feature map, which is just a new version of the image that highlights exactly where that filter found its specific pattern. So for LeNet-5's first layer, it's not just one filter. No way. The network uses 6 different filters to look for 6 different features, all at the same time. And what that does is it turns our one single input image into 6 different feature maps. Pretty cool, right? Each one is highlighting a totally different aspect of that digit. Okay, so the network has found some basic features. Awesome. But now it's got 6 full-size maps to deal with. That's a lot of data. The next step is to make all this information way more manageable. But, and this is key, without losing the important stuff. And that's where the S2 layer comes in. This is our first subsampling layer. Its whole job is to take each of those 6 feature maps from C1 and just shrink them down, compress all that information. Yeah, this downsizing process is also called pooling. And it's not just about making the network faster, though that's a huge plus. It also makes it way more robust. See, by summarizing these little patches of pixels, it helps the network recognize a 3 even if it's drawn a little crooked or it's not perfectly centered. It's smart. So what you're seeing here is the core rhythm of the first part of the network. It's like this 2-step dance: hunt and downsize. Layer C1 hunts for the basic features, creating 6 maps. Then, boom, layer S2 downsizes them. Then it does it again. Layer C3 hunts for even more complex features, creating 16 new maps. And then, you guessed it, layer S4 downsizes those. With every cycle, the information gets richer, smaller, and a whole lot more efficient. Okay, so after all that hunting and downsizing, the network has basically distilled the original messy image into this compact, super feature-rich little packet of data. Now it's time to put all the clues together. It's time to make the final call. So all those features from the last layer get flattened out into just one long list, and that list gets fed into the final layers, the fully connected ones. You can think of these layers as the network's brain. They're weighing all the evidence, kind of asking, okay, given everything we've seen, how likely is it that this is a 3 versus, say, a 9? And the entire network, this whole complicated journey, it all funnels down to a final output layer with exactly 10 nodes. So why 10? Well, it's simple, right? One for each possible digit. 0, 1, 2, all the way up to 9. So each of those 10 output nodes spits out a probability score. It's a competition. And the node with the highest score wins. If the node for the number 3 lights up the brightest, that is the network's final answer. The journey is complete. We went from a messy grid of pixels to a confident classification. Done. I mean, it's just such an elegant process, right? Especially when you remember this was designed over 3 decades ago. So why are we still talking about it? Why is it so important? Let's zoom out and take a look at the incredible legacy this architecture left behind. Okay, so here's the bottom line. This is why LeNet-5 matters so much. It didn't just solve one little problem. It literally created the blueprint for modern computer vision. This whole idea of stacking convolutional and pooling layers, that's the bedrock of the powerful CNNs we use for everything today. It proved that a network could learn to see and recognize complex things just from raw pixels. And that principle, it's at work every single time your phone unlocks with your face or a self-driving car spots a stop sign. So, you see, the story of LeNet-5 is way more than just a history lesson. It's really a testament to a powerful idea, an idea that fundamentally changed how machines see our world. It taught them to read our messy, human handwriting. And it leaves us with a really fascinating question to think about. What are we going to teach them to see next?